paper in PNAS that's about sort of how people end up with the network structures that they have, and there's some data released with that. So I'll kind of highlight that. This, I think I'm not going to talk much about unless we kind of get people are interested in it, that now is out in Nature Human Behavior, and actually has 2 letters to the editor that people have written about it, disagreeing with us, but it's okay. Actually, attention. So hopefully there's going to be a bit more back and forth about that paper shortly. And then this paper that's this kind of pretty straightforward field experiment that we did on Twitter that I think will be interesting. Okay. So I'm happy to take questions throughout and kind of just have a conversation about any components of this. So just to kind of sum up a bunch of the sociological evidence, there's been this idea, at least since Granovetter's influential work, that strong ties where we have high time or emotional intensity or intimacy, a lot of reciprocal exchange, are typically embedded or more likely to be embedded in closed triads. Right? And so according to sort of an extreme version of what Granovetter says, this triad, if the tie between A and B and between A and C, if those are both strong ties, then this triad is forbidden in some sense. That's not necessarily him saying that it never happens, right? But there may be all kinds of pressure for this not to be a stable state, right? That somehow there should be maybe a weak tie at least that forms between B and C, right? Or alternatively, there could be some dissolution or weakening of these ties, right? At least in a lot of cases. And so then on the other hand, weak ties that might not be subject to those same sort of pressure, the same kind of psychological or sociological kind of pressure to be in these closed triads, they could be more likely to be part of open triads, and that, ones like this, and thus provide access to novel, non-redundant information, right? So if I have a tie with somebody that I don't share any mutual context with, they may be providing me access to additional information and opportunities that I don't really have another short route to. Okay, so the idea there is that there's these information advantages from having a kind of structurally diverse local network. Okay. And so this, against that background, we sort of have been investigating a few different things in this area. How do different processes like disease, information, behavior, how do they spread through different network structures? Do they spread more rapidly through more clustered networks like on the left, or more random networks like on the right? We kind of know that disease and sort of information processes can spread much more quickly through this sort of a structure, but a lot of work has argued that social contagions might spread more extensively through these kinds of more reinforcing networks. In the kind of the paper, the controversial paper that I'm not going to talk about, we basically show that the answer is this, even for social contagions, if you have more realistic models. Then related to what I just said, we might wonder about the individual perspective, right? Is having a particular kind of local network structure one with more closed triads around you, or one with more of an open, structurally diverse structure, which one of those might be more advantageous, right? So is gold better off than red, right? And if we thought that, these structures were giving people access to information and they're going to have access to more diverse sets of information, we might expect that about the gold node. And then, somewhat, if we say take for a moment that as given, hey, it's better to have a structurally diverse network, it might be a little bit of a puzzle why real empirical social networks have so many closed triangles. Right? Why is it that it seems like there's just an excess of closed triads in real social networks, and that people are constantly sort of closing open triads, right? That might seem like a bit of a puzzle, right? And so then related to that, you might wonder, why do some people end up deviating a bit more from that and having more structurally diverse networks? How does somebody end up like the gold node here rather than the red node? So just to kind of give us a sense of what the state of our knowledge is here, observed social networks do indeed have lots of closed triangles, and really more than would be predicted by simple random graph models. So certainly more than would be predicted by something like an Erdős-Rényi graph over the whole set of nodes, but also sort of extensions of that, models with homophily that you can think of as having this block Erdős-Rényi type structure like stochastic block models. It seems like there's often too many closed triads there. But there's some ambiguity to this because depending on exactly how you might parameterize these stochastic block models, in some cases you might be able to sort of explain away the level of triadic closure simply through positing that people share some kind of latent characteristics, right? So if we make the blocks in a stochastic block model smaller and smaller, we might really be able to explain why there are so many triangles. The people with all these dense parts of the network, they all share some latent characteristic with each other. And so it could be often hard to rule out a sort of alternative explanation for high levels of observed triadic closure, which would be people who have all these closed triads are just really similar to each other in unobserved ways, right? And so these are some results from this paper by Abaca Ramirez and Peixoto, where they're looking across a whole collection of different networks. And so each point is a network's observed clustering and deviation from a degree-corrected stochastic block model fit. And so this is in relative terms, and then this is sort of z-scored. So only the ones outside of this range are ones where we're like really extremely rejecting this model. So there indeed are a bunch of networks where it seems like there's kind of too much clustering and thus too much triadic closure to be explained by a stochastic block model. But again, you could further tune or overfit maybe the stochastic block model to the data in a way that might explain more and more of the triadic closure. So really what we want to understand here is, yes, observed networks have lots of closed triangles. How much of this actually reflects some kind of disposition towards triadic closure? So sometimes this has been cast in different ways. People have sort of, talked about structural homophily versus preference homophily, or try to distinguish choice homophily from other factors, right? It might be that we can only form a tie, in certain contexts if we've met before, right? So, or if someone has introduced us, or if of the millions of, users on social media, if I discover your account or not, right? So there could be all these factors that determine even the kind of possibility of forming a tie. That means that when we, observe a lot of closed triads, that might not indicate that anyone has any preference or even a disposition or tendency towards closing triads. So our goal in this work was really to get kind of a very clean, causally credible estimate of some, potential disposition towards closing open triads. So we're going to be working in this kind of a setting. It's a directed setting. We're going to do an experiment on Twitter. So A is a bot that we control generally, but in our specific experiment. But you can think of this a little bit more abstractly, right? If C follows B and perhaps B follows C back, maybe they do, maybe they don't, right? And then A follows B, and B reciprocates the relationship with A. We now have this, this open triad, especially in one relevant direction. C follows B and B follows A. So there's this kind of transitivity, right? Is the presence of these edges, especially the edge from B to A, is that going to cause C to follow A? Right? So that would be then closing this triad, right? One of the things that's interesting, as soon as you go to a directed network, there's so many more possible combinations of things, right? There's so many more ways for this to happen, right? I think in this particular version, we're thinking of, the direction of this as being that, C, this blue line indicates that C follows B. Of course, you can actually draw the arrows in the opposite direction, and then you'll be talking about everything in the opposite direction. That's just kind of, notational choice, basically. So I think one interesting, some of the best current evidence that we have for this kind of a process, right? So I'm actually open to suggestions there where we're looking to add more related work to our paper. I think of some of the evidence as this kind of cross-sectional evidence that I showed here, right? That you have this model. There seems to even be conditional on some model. There's an excess of closed triangles. I think another category of evidence comes from longitudinal data, where you have you're observing a network over time, and so you might be able to observe that we see these edges form at one time, and then we have both data from this time period and data from this time period, and then shortly after this time period, that's kind of associated with these edges forming. And we might be able to control for a bunch of other characteristics. For example, Kosinitz and Watts have a influential paper from 2006 and another one from 2009, where they are studying the email network of Cornell University, and they can say also control for the fact that A and C might be in the same class together, and so they could say right. So what might be jointly explaining this whole process is that they're all in the same class together. I think part of what remains ambiguous, even in the longitudinal data, is often the network that we're using. It's unclear whether that particular network is playing a causal role here, whether there's actually pressure from this triad, or whether somehow this triad is like just causally downstream of some other network, right? That we're having in-person interactions. And in fact, all three of us have already interacted in person, but only A and B and C have emailed each other or sent text messages to each other, right? Or, of course, the reverse. You might be analyzing really rich mobility data and see that, A and B have been together and B and C have been together, but they haven't all jointly been together, but they were all on a WhatsApp thread together, right? So we might really worry that even if we thought we've done a super good job of controlling for all the things we might think of as confounding factors here, social foci, that the network that we're studying is not actually exerting any sort of causal effect in the direction of closure. So this sort of motivates us approaching this through a field experiment. But actually, I'm really interested if people think of other evidence that they think of. No, this is how we have evidence for a causal role for open triads in producing edge formation.
Well, I know it's causal, but a lot of people are working in the prediction.
Right.
And one of the predictors is the number of common friends.
Right.
Which is the number of triangles you are part of.
Right. Yeah. Right. So yeah, I would think of that as also sort of, a lot of times that's this as well, longitudinal data. You're seeing this, sometimes people set up these link prediction studies as things evolving over time. There's actually this cool papers on closure coefficients. I don't know if people have seen these by Austin Benson and Yuri Leskovich and their student, whose name I'm forgetting, I think went to finance. And one of them that's on directed closure coefficients is also with Johan Ugander, who's, I guess, coming here in a little bit. And they really focus on, okay, what might produce variations in the disposition to close these kinds of triangles. And when we think about explaining whether this closes or not, who should we think about it from the perspective of? Usually, clustering coefficients, like a local clustering coefficient, looks at B and it says, hey, how many of these wedges around B get closed? Or how many of the wedges are closed in cross-sectional data, right? So that's like a clustering coefficient. But that might not actually capture the behavioral process. That would explain a behavioral process where it's like, hey, does B introduce their friends to each other, right? Do I host dinner parties where I bring together people who don't know each other, right? But it might not explain, if one of the big sources of variation in this process is sort of something active by C, where they're saying, I want to become friends with my friends of friends, right? And it's their personality characteristic is basically to close triads that they're at the end of, right? Rather than that they're at the center of. And they find by basically looking at longitudinal data that it seems like this kind of closure coefficient computed on C that's about, how many of these cases they've filled in, right? That's much more predictive of future links forming than the heterogeneity at the B level. So Yeah, so I think there's something certainly very informative about that, but kind of not maybe as clean and unambiguous as what we're aiming for. But yeah.
I have something that I'm working on, well, it's under review right now, that looks at sensitivities, causality from the point of view of
Uh-huh.
And we find that amplification by, I guess, B in this case, of A is C to follow.
Yeah. So in some contexts, it might be B's propagating C's content in social media or something, or.
Yeah, B would be propagating A's content such that C sees it,
right.
C is already following B.
Yeah.
Sorry, that's a lot of letters.
Yeah, no, but I think that's a very natural thing to think about. Yeah, that's interesting. Cool. Yeah, love for you to send that to me. And if people think of other things later, really definitive prior work that makes this whole thing redundant, do send it to me. So,
if not, then right. You did the survey and no one could come up with it.
Yeah, exactly. Yeah, we're in the process of revising this paper and really trying to better state the situation in the literature. And I think for a lot of people, and I can relate to this idea, they say, of course, there's a disposition for triadic closure. No one has ever doubted this, et cetera. So we're kind of trying to highlight some of the gaps in the existing evidence here. Okay, so I'd say there have been some interesting related experiments getting at homophily. To what degree do people actually, homophily, love of the same, right, does suggest a causal role for similarity. It's not just about, that people are happening to encounter each other, right? And so sometimes people, then are thinking about, preference homophily versus structural homophily, right? So it could just be that we have more opportunities to interact with people who have a bunch of similarities to us. And that could explain a lot of the observed assortativity in the network. I use the word assortativity just to sort of designate something that's just purely correlational. People have correlated traits that may not reflect any preferences that they have for forming ties with similar others. But Tianshu Sun and Sean Taylor ran this cool experiment in collaboration with Facebook, where Facebook was introducing this thing on profiles that they called things in common, basically, that you're viewing somebody's profile who you're not yet friends with, and it might highlight, not just mutual friends that you'd have, but other things you could have in common, right? LinkedIn does this kind of thing all the time. They say, oh, you both worked at, Yahoo together, right? Or you both worked at Yahoo, but maybe not during the same time period, right? So this could be a mutual hometown, interest, education, work, or city. And so then they're fixing, I'm viewing somebody's profile who does indeed have a thing in common to show me. I'm just going to randomize whether I'm showing it or not, right? So I'm already at the profile. Whatever structural factors might be affecting whether I end up viewing somebody's profile or not based on our similarities, those we've all conditioned on. We're just going to randomize whether we show this things in common. And so, here you actually have one thing in common, and you can either not show it or you can show it. And showing it increases sending a friend request by 2%, and actual formation by a bit over 1%. If there's more things in common, right, there's kind of a bit of a larger effect, but we can't directly compare these because this is sort of the spaceline difference in how similar we are. So this experiment is the kind of thing that we'd like to do, but this experiment doesn't randomize mutual friend info. They're randomizing the presence of other things in common info. In a similar experiment with this kind of the same team, Mohsen Masla, David Rand, and I, and then in this case also with Cameron Martell, we were trying to probe the degree to which there's real partisan homophily versus just partisan assortativity online. Do people seem to be connected to and following co-partisans on Twitter, but is that because they actually have a preference for that, or are there other factors? So we created partisan bots on Twitter and then randomly followed co-partisans or counter-partisans, people who we estimated to be on the left or the right in American politics. And so, then we're looking at the probability that they reciprocate our tie formation. So we're following them. Do they follow us back? right? And if they're co-partisans, if they're assigned to be randomly assigned to be followed by the co-partisan bot rather than the counterpartisan bot, they have a much higher rate of following us back than if they're counterpartisans. Okay, so this is then this kind of like clean, evidence for this dispositional or preference homophily in partisanship in online networks. And this is sort of what prompted us to think about doing this study that I'm going to mention, is that basically we said, hey, like, what if, since we can get some of these people to follow us back, what if we look at what happens as we keep following people in their neighborhood, right? And that could allow us to get at questions about this sort of dynamic causal process of triadic closure. Okay, so here's the experimental procedure. We created a bunch of human-looking bot accounts. We're going to call those the A users. Maybe we should have called them the B users because they're bots, but sorry, they're the A users. They then follow a sample of Twitter users, B users, and the B users follow us back. So actually, technically, the B users are the ones that follow us back of the many that we follow. Okay, so 200 some follow us back. Of the followers of those B accounts, right, then there's a bunch of people following these B accounts. We randomly sampled about 7,000 of them who followed only one of the B users, right? So we don't want them to be exposed to us interacting with multiple of the B users. So these are all people who follow a B user and exactly one. We're going to call them the C users. You should think of them as basically these subjects in our experiment. All of this we're sort of conditioning on, right? And now we're going to do things that are going to potentially affect the C users. So we now randomly assign these C users to different conditions. They're either followed by a bot account with whom they share a tie. That's the open triad condition. You can think of that as our treatment condition. And then we basically have 3 different control conditions that I'll kind of explain that I think deal with some other worries you might have here. So this is kind of a diagram of how this all works. So in the stage 1, we form the open triad so that A ends up with this open triad with C in what we think of as in the right direction, right? Is that C follows B and B follows A. We have multiple bots. So there's also an A prime here. That's a bot that didn't do any of this stuff, but it's very similar to the A bot. Then we, at the level of B users, we can either destroy the ties between A and B or not. So we're going to randomly assign some of these ties to be destroyed. You can do this by blocking somebody and then quickly unblocking them. Ties in both directions are destroyed by that. So, so that's sort of one randomization. So in one of these versions, we then have deleted that structure. Now, in the case where we don't delete the structure, we can actually then say we're going to have either A, which does have this open triad structure, or A prime, which never had it, follow C. And then we're going to see whether they're reciprocated, right? So basically we have, this open triad condition where there is the full structure. We have this, what we call the never triad condition where there is this triadic structure there, but not for the bot that actually follows C. So the one that we're looking at whether they reciprocate with is a different bot altogether. Then we have the broken triad condition where we've actually destroyed these edges and they're really being followed by this original bot A. And then we have, just because we did this in a factorial way, we have the combination of the two, right? Why did we do all of this? One big thing, and this is just like maybe interesting from an experimental design perspective, the broken triad condition has to be assigned at the level of B users, right? So all the C users associated with the same B user are going to get the same broken triad or not assignment. And that means that it's this cluster randomized experiment, and we might think that that creates a bunch of dependence. Maybe a lot of the C users who share a B user are similar to each other and are either the type of people who reciprocate or don't reciprocate. And so we might worry that that's sort of going to give us less statistical power if that was the only control condition we have. If we're just, because then in some ways our randomization unit, we only have 214 of. We only have 214 B users. So then, we sort of have in some sense, an N of 214, maybe, if there's a lot of dependence among C users who share a B user. The never triad substitutes a different bot for the original bot. We made the A prime bots as similar as possible, including in followers. We had accumulated a bunch of followers that we kind of paid for and also through following a lot of other people. But unlike the A bots where we broke the tie, we can't really rule out that they're somehow different through randomization. So that's the reason for all these control conditions. And we pre-registered that we were going to test whether the control conditions were distinguishable. And if not, we'd focus on just the treatment versus all of the controls pooled together. But I think that's maybe in some ways this is a very simple experiment. In some ways it's a more complex experiment, but we kind of hopefully made the analysis sort of simple by doing a bunch of like more complicated things up front. So including that we also did stratified randomization. So we used a procedure called threshold blocking to form strata, both at the level of B users. So there's similar B users some are being assigned to treatment, some are being controlled in a balanced way. And then also for the C users, just sample some of them because there was so many of them. We couldn't follow all of the C users without Twitter, stopping us. And so we also were doing sampling there. Okay. So here's what kind of the stimuli would look like, right? Is that Bruce Draper has just followed you, says follows you. And either you see he's followed by David Oliver. So you're the C user, you're viewing the A user's account, and they're saying that they're followed by the B user, or not followed by anyone you're following. Personally, I have a very strong preference for running experiments that involve changing tiny gray text. One of the things that's nice about this is like really when you think about the kind of how clean or causally unambiguous this all is really mainly all we're changing is this text. Now, if we were sitting at Twitter, we could just maybe randomize this text in some way. We weren't in a position to do that. Now, there are some small ways, I think, related to what you were mentioning of this amplification. If we had, say, the B user was retweeting the RA user, there might be some other effects possible. So it's not necessarily that it's just that light gray text, but we think basically it is because RA users are sharing some things, but they're not sharing that much. And on average, the B users are not necessarily retweeting them that often or anything like that. So it is possible, but we think, especially because we're really looking at a period, immediately following, Bruce, our A user, following the C user, that it's mainly driven by basically this stimulus when they kind of see that they've gotten this request. Okay, so what are the results? Here's the rate of reciprocal tie formation, the fraction of the people of the C users who reciprocate forming a tie with our A or A prime account. So first, the control conditions end up being indistinguishable from each other. And so the open triad causes 3.3% of C users to reciprocate. And that's a relative increase of about a third. So it's about like a 35% lift in reciprocal tie formation. So this suggests that, at least in this context, right, this is this very minimal context. It's not, there's not tons of other things to recommend our accounts, right? It's not like our accounts are celebrities or that people are going to know our accounts by other means. They're not encountering our accounts because they're producing highly original content or something like that. So it's against the background of accounts that are not necessarily super compelling on their own. But I think against that background, this is really a pretty substantial effect in terms of the change in tie formation. You can kind of break this out and really look at this. How many bots did we have? We had 8 different bots. There's pairs of A and A prime bots. And so you can look at these results for each of the pairs. Those are the overall results that I showed you. And then for each of the bot pair 1, 2, 3, 4, and we didn't set up the power of this experiment to ensure that each one of these is going to come back statistically significant. But I think this helps helps illustrate the kind of structure of this experiment, right? Is that there's these 8 different A or A prime accounts producing these overall results. Cool. Questions about that so far? Yeah.
Okay, one initial question. Did you do that on slide? Looking at little green machines?
Yeah.
How were you able to control whether or not the people that are shared followers are showing up their bots you care about? Because in the case of multiple shared followers, that was the same. super short, and I'm not actually sure what's listed.
Yeah, so all of these would be cases where there are no other shared followers. And the way that we did that is by initially eliminating all the candidate C users who followed multiple B users. And then, so that's, and then as these ties formed, we actually blocked all the C users and unblocked them so as to break all of those ties, so as to not affect the other C users. The way that we're doing the statistical inference, I think, is robust to whether there is such a dependence there, whether all the C users are somehow coordinated. But basically, we're doing that to ensure that there's sort of only ever one person here, right? So we finally get this A user to follow it, or the C user to follow our A user back, and then we immediately destroy both of the ties.
But what you're not controlling is the follower count, because it's actually different bots and different people might follow different bots.
Well, so I would say that's part of the reason why we like the actual destroying of the ties condition, is that the A prime bot and the A bot might be subtly different. They actually do have very similar followers, in part because we're constantly destroying all these edges that we're creating. And they were all sort of had followers that we had purchased to the same level. And so since we're constantly destroying the edges that form, we don't end up with this like higher edge, this higher follower count for the A bots compared with the A prime bots. But I agree, that's basically one of the main reasons why we really wanted to have, this whole arm of things where we actually we're gonna follow you with the A bot, the bot that really did have this whole interaction with B. We're just going to destroy that relationship and then follow you. But yeah, I agree. Basically, these contrasts might make you worry about that. One sort of thing you could think of as a control for whether that's a big issue is this contrast here, right? So, this contrast, the never triad condition, and then, versus the broken triad condition, right? These two are both control conditions. And if there was something different about the A prime bots compared with the A bots, we would expect it to show up here, right? But we don't detect anything, at least. Okay.
And you say that you never have more B's, say in between the bot and the C's, right?
Right. Yeah, we selected the C's so that they are only following one B account. Yeah.
This condition might be that was the most difficult part probably of designing this way, right? Mm-hmm. To find C accounts that only follow one B.
Yeah. Well, so these B accounts came from this very large set that we initially followed. I don't have that here, but I think it's, it's going to be like 5,000 or something like that. So we followed 5,000 people. 214 of them followed us back. And then we're looking at their followers. And these B users are not like superstars. In fact, we actually, just to be clear, we exclude B users who have over 10,000 followers. So these are sort of potentially pretty active, reasonably influential Twitter users, right? But they're not like superstars in some way, right? Whereas if we somehow had in the step of the B users, we'd gotten, Elon Musk to follow us back, or in this time period, Taylor Swift to follow us back on Twitter, right? Then then we'd have that problem in droves. We'd be celebrating for other reasons, and we'd be maybe doing something else with these accounts. But we sort of avoided that problem through our, we didn't even attempt to follow people who had a ton of followers. So
I'm saying this because 2 steps from you in Twitter.
Right, a lot of people. But you
have a lot of people that have a large degree.
Yes.
So selecting people C's that only follow one B might be
restricting something in some way.
Yeah.
Yeah. Though the thing is that basically these B's are not super. Say if the B user has at most 10,000 followers, and there's a lot of users on Twitter, compared with 10,000. A lot fewer than on like the other more important social media services, but yeah.
Did you use these findings to make your attempts to follow B users more effective? We got 5% follow back rate or something?
Yeah, I think that's interesting. And actually, so Tawhid Zaman, who's at Yale now, he and David Rand had done a little bit of work in that direction. He had done some work separately, more from a more like sort of optimization perspective. If you had some beliefs already, you had some model of how you're going to get people to reciprocate with you, in what order should you follow people so as to get a target account to follow you back? So if you want Taylor Swift to follow you, who do you need to follow first? You don't start off with following Taylor Swift. You follow various other people to get them to reciprocate, and you kind of keep going. So, yeah. Cool. So we looked at whether there was a little bit of, whether there was some heterogeneity in these effects, right? So are there characteristics of the C users or of their relationship with the B users that might affect whether there is this kind of disposition towards triadic closure, right? So we have, this open triad treatment, and then these are just separate linear models predicting whether there's reciprocal tie formation with our treatment indicator, then a relationship between B and C users, and then the interaction of the open triad treatment with that relationship. And so the one that comes back as being statistically significant and quite substantial is that if there's if C is mentioning or retweeting B more often, then this effect is stronger, which makes sense, right? So if B is somebody who I actually think about a lot, and then when I'm viewing this profile that just followed me, I see that B follows them, right? Then it makes a lot of sense that I would think of that as much more of a important endorsement. So you can kind of see that visualized here in terms of the mentions and retweets of B by C. These are the quintiles, and this is the reciprocation rate in treatment, and all the controls bundled together. And there's you can kind of see this somewhat more non-parametrically here. But overall, we basically did not find much heterogeneity in this effect. I mean, we weren't necessarily set up in terms of our statistical power to do so. I'm just showing you 3 variables, but in the paper, we have a bunch more, also some variables at the level of C users describing their activity. A lot of those things do predict reciprocating, right? Like this common followers and followings. That predicts reciprocating because it's telling you something about the local density, how much C just like kind of follows lots of people, but it's not it's not telling you about some difference in the treatment effect. Cool. Okay, so that's the main result of this paper. In some ways, it's kind of simple. You might think, I started this talk believing that people have a disposition or tendency towards triadic closure. Triadic closure is a thing. Now you're at this point in the talk, I've shown you the data. Yes, triadic closure is a thing. So I don't know, maybe that's not, I don't know. We'll see whether that's compelling or not. But I think perhaps along the way, it's kind of, we've highlighted that there's a lot of ambiguity about exactly why there are so many closed triads. And I really like the kind of just simplicity of this. This is like this sort of minimal effect of, or minimal process by which you might get this sort of effect, right? There's nothing like, B is not exerting any social pressure here. There's no social pressure to like follow our bot account, right? There's nothing like that. There's situations that they're placing them in together. There's no other network that might be relevant. A only exists in this one network, right? They're our bot account, right? So it's all coming from, the presence or absence of these edges, which mainly is reflected through this tiny light gray text. Okay. I don't know if there was other questions.
Do you have an explanation for so what's the mechanism? Why do people reciprocate?
Yeah, so I would think about this, one framework we can use actually for this kind of whole thing is, thinking of it as very related to the problem in peer effects of distinguishing homophily from contagion or homophily from peer effects, right? That we're often always concerned that there's some kind of latent characteristic of the people, right? That's explaining why you do something and then why I do the same thing. That's not you causing me to do it. We're exposed to common shocks. We have a bunch of unobserved characteristics that are making us do the same thing. And so I think of this in very much the same way. So all what we've been doing, you could think of as this is a study in social influence, right? The behavior of interest is following the A account or reciprocating tie formation with the A account. And so we're looking at this kind of influence. So then you can apply some of the same taxonomies of different reasons for peer effects that appear in the literature. So Mansky has this article from 2000 where he talks about kind of different sorts of social interactions, a term that economists would sometimes use to describe peer effects or influence. Constraint interactions, expectation interactions, and preference interactions. And so, constraint interactions could occur if you do something and create some knowledge, and so it removes a bunch of constraints, perhaps, right? Could also do something like you create a bunch of traffic by driving, or you get in line in front of me, and now I'm not going to get my coffee in time, and so I decide not to get my coffee, right? Expectation interactions would be cases where you do something that changes my beliefs about maybe the benefits of taking some action, right? So that by you doing it, I sort of get the idea that maybe I'm going to be better off from doing it, and I might even observe the outcomes from you. I might see you do something, and then it work out well for you, right? So that'd be expectation interactions. And then preference interactions would be I actually have some kind of preference for coordinating with you, or in some way my utility function directly incorporates your decisions, right? Which would be like if we're considering adopting a network product where there's a product that has network effects, right? My choice to adopt WhatsApp depends on whether other people adopt WhatsApp, right? Or if they're using Telegram instead, right? So I would think of this as mainly driven by expectation interactions, right? There's not really, our A accounts are not doing anything super exciting. It's not like you want to be around the water cooler with B, kind of talking about whatever A is doing. A is not doing anything very exciting, right? Also, a lot of these relationships are sort of only really existing on Twitter. And so there's not a lot of room for social pressure. Certainly A is not going to exercise much social pressure here. So there's not really this kind of network effect or expectation interaction. The constraint interaction, you might think of something like that as actually that's how you've somehow found out about A because this constraint interaction has been relaxed. Because you might think, well, in fact, which is what did happen, A only found C because B reciprocated following with them, right? A is our account, but our algorithm is only finding C's who follow B's, right? And so indeed, the B's behavior has done that, but we're conditioning on all that. So that can't play a role there. So I would think of this as being this expectation interaction where this functions like this kind of minimal endorsement, right? This is saying, hey, this might be a reasonable account to follow, right? And so there's sort of, you might consider doing the same thing. So that's a little bit how I would think about that mechanism. I don't know. What do you think?
Yeah, no, I like that explanation. That rings true, and it's maybe sprinkled over a little bit of fairness, right? Like you click on this random profile of this person that followed you, and it's odd, it doesn't mean anything, but then it stands out because someone you follow is shown there.
Right. Yeah, that says like, oh, maybe this person is interesting. Yeah. I mean, I would say we can't conclusively rule out that there's some preference interaction here. It might be that I want to get closer to B. I'm the C user. I want to get closer to B in some way. And I think, oh, well, Bruce, that's somebody that B also knows. And maybe if I start interacting with Bruce, that, the B user also, his name starts with a B, Bob is going to want to interact with me more, right? So I don't think we can completely rule that out, but I would guess most of it is this kind of expectation interaction, or psychologists using a somewhat different typology would probably call this like a informational influence as opposed to normative influence. Yeah.
I guess given the time constraints between all of this, was it easy to isolate and remove the algorithm exposure potential? Like, I don't know how Twitter's algorithm works for recommending new followers. If it's they actually use this kind of
right.
They use it.
Yeah. I think because we're kind of deleting things, that's really helping, and because we're basically, if somehow, I don't think this ever happened in our experiment, if somehow a C user managed to follow our A user before we follow them, they're not in this data, and I don't think that ever actually happened. But So that would be a sense that something like that is happening. You could imagine something like, oh, they saw Bruce in the algorithmic recommendations before, and then now they're seeing that Bruce followed them, and so now this is sort of like this reinforcing signal or something like that. But I think we don't know whether Bruce showed up in any algorithmic recommendations, but we think probably not. I mean, really, from Twitter's perspective, there's a lot of signs that these are not particularly great accounts. So it's not, but yeah, I think we can't completely rule out that there's some process there. But we've tried to minimize it by basically all this, blocking. Yeah.
Nerdy technical question. What's the time frame of the following and the reciprocating? Because you're measuring this increased rate of reciprocation.
Yeah.
But at some point, you need to cut off your observations, right? Like maybe they're still going to reciprocate.
No, and it might be nice to actually show that effect over time, like some sort of hazard model analysis where we could have in continuous time.
If you will, right? Like your effects are conditional on your time cut. They might go away if the experiment run long.
Yeah. Well, I think the way that there's a couple ways they could go away. One is that they follow the A account anyway. I think that's not, I think basically they get followed and then people reciprocate on a short time scale. So, and I don't see them coming back to the A account. You might imagine that there could be a larger effect of the open triad in the case where they are browsing to who does the B user follow, and then they might rediscover our user. But yes, I think that's actually just an important thing for us to clarify that. But yeah, I think it's this is on the order of days. Yeah. Cool. Okay. Oh yeah.
Can you talk me both to the end information on when within those 28 days?
But when they reciprocated?
Yeah.
Yeah. Oh no, we have that, which is why I'm saying actually we should just produce that plot. We have some time windows. I think we don't know the exact timestamp because but I think we do have, maybe we do. I don't know. So also, I mean, I'd say a lot of the details of working with the Twitter API is something that Mosa Masla is an expert on, and that I am totally not. But I believe that because I've done some of the data analysis for this, I believe that we have those timestamps in there. So I think that would be a great thing to look at, in part just understanding, kind of how quickly that happens. And you might think, that it's all happening in a pretty short period of time.
In our paper, we have the kind of time slice window analysis too, right? And if the window is too short, there's not really an effect because there wasn't enough time to do anything. If we let it run for too long, then it kind of goes away because things would happen anyway.
Yeah.
So
I think in this case though, things don't happen anyway, right? There's basically after the initial chance that they have to reciprocate with the A user, nobody is going to somehow follow our A users. And I believe eventually we deleted the A user. So in some sense, that means that the effect went away. It deleted the A users. In another sense, it means that, the effect persisted indefinitely. No one was ever able to reciprocate with our A users after that. So, yeah. But no, I think it would be great to sort of look at that kind of envelope of that. Yeah.
And after the retweet, and then in the subsequent days,
Right, which I guess would be, some of that, it depends on whether you think of that in terms of cumulative effect or that time slice effect, right? Because I would assume that basically this effect goes away in the sense that in a given time slice, the additional hazard is going away, but the cumulative hazard is all generated in this initial period. And so there's going to be a difference in cumulative hazards. But basically, I would assume that, you get a notification when this person follows you, not necessarily a push notification, but on-site, an on-site notification. And, either you sort of act on that in that time window or, not really. So I would assume most of this happens in like the C user sessions immediately after this being followed. But I think it's a good thing to check. Of course, we don't know exactly when their sessions are because, we don't have their login data. We know when they're active, but we don't, when they're posting things, but we don't know otherwise. Okay, so that's kind of this main experiment. I wanted to just mention, maybe because it's more related of this thinking about where are a lot of triads closed. And so this is in some ways just a little bit of an ad for some data that you might want, which is that we've released for every zip code in the United States and Mexico a measure of how many long ties that they have. That is, how many ties these people have on Facebook with people who they don't have other mutual contacts with. And also their clustering coefficient, and also versions of this that are weighted by tie strength. And so, you can zoom in and look at, where Boston is on this fraction of long ties, and also on the weighted fraction of long ties, which is sort of capturing the degree to which they have higher tie strength relationships for which they lack mutual ties, right? A lot of times people think of weak ties as being cases where I, don't have mutual contacts, right? But that's sort of a separate dimension. Weak ties are associated with having, with being long ties to people that I don't have mutual contacts with, but they're not the same thing. And so you can actually have strong long ties, and the people who do have these kind of stronger long ties have better economic outcomes, and the places have better economic outcomes. We in the paper analyze individual level data as well, but what we've released is basically this data where for any given zip code, you can look up this measure of the fraction of long ties, weighted fraction of long ties, a clustering coefficient, and a weighted clustering coefficient, where the weights are by how many comments or mentions those people have exchanged on Facebook. So, this somewhat gets at this idea of like, hey, there's this growing evidence. This is, very observational, cross-sectional evidence that people get a bunch of advantage from having more structurally diverse networks, which sort of makes it interesting, thinking back to the Twitter experiment, right? People are actively following people that are kind of redundant sources of information, right? I'm paying attention to what B posts. If A was posting anything super interesting, maybe B would just retweet them. But then I'm seeking out to follow A directly, seeking out to sort of have this redundant network. And it sounds kind of related to what you were finding as well, which I think is interesting. It makes a lot of sense from this like endorsement perspective. Maybe B isn't retweeting everything that's interesting, right? But on the other hand, it's a little weird because it seems like I don't need to, cover this exhaustively. I want more, if I was thinking this from information diversity, I want some kind of, to solve some covering problem over all the interesting things that are happening on social media. So I'd be following one person over here, one person over there, et cetera, right? But that's not what people are doing. And they seem to have this disposition really for actively building this kind of more redundant information network. So anyway, I think I'll conclude there and just highlight that I was mainly talking about this. There was this work with Mohsen Masla and David Rand. And I'd encourage you to check out the data for this other paper. Thanks a lot for all the cool questions.